Okay, so in this talk we'll be looking at how we can use measurements of surface deformation made by optical image correlation to estimate the co-seismic stresses along large magnitude surface rupturing events. So some of the questions we'll try to address in this talk are what is the degree of variability of the co-seismic stress orientation along a rupture? Can we place some kind of bounds on the extent or degree of variability along a rupture? The second question is how similar are the orientations of the inter-co and post-seismic stresses? For example, are there significant rotations from the far field to the near field along faults that are thought to apply to weak faults like the San Andreas? And can we detect the effect of dynamic or topographic stresses? So to try and answer these questions, we use optical satellite imagery taken before and after an earthquake. We then apply subpixel image correlation method to measure the co-seismic slip vectors, which we then invert for the co-seismic stress tensor. So the overall aim here is to try and understand whether we can resolve spatial variations of the co-seismic stress orientation along ruptures using this 3D optical image correlation technique. So to measure the surface deformation pattern, we've been developing a correlation method that can use a range of different satellite sensors. And so the way to measure the 3D surface displacement field is it essentially involves triangulating the 3D position of each pixel in space before an earthquake at time 1 and after an earthquake at time 2, and then essentially trying to track how that 3D pixel shifts in space over time. And so the way that works in detail is if you have stereo pair images taken before and after an earthquake, you can correlate between these pairs before the earthquake. You can correlate a pair across the earthquake and correlate a pair after the earthquake. That gives you 3 displacement maps, each with motion in the X and Y direction, or north, south, and east-west direction, which gives you 6 independent measurements of displacement. And so with those 6 independent measurements of displacement, you can invert for the 3D co-seismic displacement and the motion due to the parallax effect, so you can estimate the elevation too. And so you're left with an overdetermined inverse problem. And so here we use a mix of different satellite sensors, ranging from worldview 1, 2, and 3, and spot 6. So we have displacement measurements for 4 different earthquakes, but I'm just going to concentrate on the 2019 Ridgecrest earthquake that happened in the Eastern California Shears in California, and the Kaikoura earthquake that happened on the South Island of New Zealand. And so the way we measure the slip vector is from each of these the 3 displacement maps, we measure the fault parallel, perpendicular, and vertical component motion to then get the full 3D slip vector. Okay, so once we have those slip vectors measured from the 3D displacement data, we can then try and estimate the stress regime following this assumption that the slip vector is parallel to the shear stress traction vector. So this is an illustration here showing how different stress regimes, if you rotate the stress tensor, can produce a range of different slip vectors on faults with different orientations. And so the idea is here is essentially if we can measure all slip vectors with different orientations, you can then use it to reconstruct the 3D stress tensor. And so this approach requires a diverse range of fault orientations in order to estimate the stress tensor. And so we estimate the 3D stress tensor using the classical method of Michael 1984 and using a least squares approach. So here's our slip vector, our data vector that contains the slip vectors. We then use it to invert for the 3D stress tensor, and we can estimate the principal stresses with an eigenvalue decomposition. And then we can also estimate the R, what's also known as the shape ratio value. And this is a fairly useful property because it gives you an idea of the relative magnitude of stresses between the different principal stresses, because we can't estimate the absolute values, the magnitudes of stresses, we only get the orientation. So this gives you an idea of the relative sizes of the different principal stresses. Okay, And so for the Ridgecrest earthquake, these are our slip vectors that we measured from the 3D displacement maps. We have both the main shock and the foreshock because our images bracket both earthquakes, the foreshock and the main shock. So you can see here on the main shock, the slip varies in rake around 180. So this is indicating right lateral slip, and then here you have rake of 0, which is left lateral on the foreshock, and then you have some conjugate faults up here. And in this region, we have some displacements that have nearly pure normals. This is a little graben region. And so inverting these slip vectors, this is our stress tensor result for inverting all these slip vectors together. Is about almost 300 slip measurements here. And so we find a sigma 1 that's nearly horizontal and trending south-southwest. And this shows and we find an R value of around 0.5, so it shows an almost Andersonian strike slip stress regime. And so from this we can also estimate the static coefficient of friction by projecting the stress tensor onto these different fault orientations. We get a static frictional coefficient of 0.7, which is quite high, indicating a fairly strong intercrustal fault. And this single stress model can explain a surprisingly high amount of the percent of variance reduction of the data. Around 92% of the data variance can be explained by just a single stress model, which is surprisingly high. And so from this chi-square value, or reduced chi-square value, we get a value about 1.4, showing that there's still some variance in the data that cannot be explained by the stress model given the uncertainty in the data. And so this is comparing our observed slip vectors shown by the black vectors, and then the red is our predicted. You can see they match pretty well. And so the percent of variance reduction for the components in the east and the north directions are quite good. For the vertical, they're significantly worse, around 30%. And this is, I think, for two reasons, because one, this is a strike slip fault, so the vertical component motion is very small. So the magnitude or the signal is very small in this component. And also the vertical displacement maps are quite noisy compared to the horizontal components by a factor of 2 to 3. So this is fairly expected. But overall, you can see we find a much better fit to the horizontal components than the vertical. And so given the chi-square test showed there's still some variance in the data that is not well explained, we tried to see whether we could partition the rupture into different stress domains to see whether we could resolve any variations, spatial variations in the stress. Okay, and so here shows the stress inversion result for the northern half of the rupture and the southern half of the rupture. And so we find that in both zones, sigma 1 is oriented, is plunging near horizontal, but the southern zone, sigma 1 is trending in a more north-south direction. And this seems to agree fairly well with what was found by Hardeback for the interseismic stresses that was estimated by inverting the background seismicity, focal maximums from the background seismicity, where in the northern half, the orientation of the maximum horizontal compressive stress is larger than 10 degrees east of north. And then further towards the south and the foreshock region, the maximum compressive stress rotates to be in a more north-south direction, which is consistent with what we find here. So it seems to be that the co-seismic stress orientations we find here seem to be generally consistent with what is found in the interseismic stress state. And so we do believe that even though we've partitioned the rupture into these two different zones, we do maintain sufficient slip vector diversity. So a minimum value was proposed to be 30 degrees to be a reasonable value to accurately estimate the stress orientation. So in both these zones, we have a value of about 47 and 77. And we also find distinct R values for these two zones. For the northern half rupture, we have an R value of about 0.3, which means the stress state is closer to being transtensional, which is consistent with what's found by Sheng and Meng, where they found in the northern half of the rupture a low A5 value, indicating it's dominated by normal faulting, and then further towards the south, you have a zone that's dominated by strike slip and some thrust faulting or transpressional stress. But one thing we found is that this heterogeneous stress model or two domain stress model only provides an increase of 1% of the percent of variance reduction over the previous model, which was 92%. And it also fails the it doesn't fail it. We cannot reject the null hypothesis under an F test that this that the additional model parameters or a more complex model can explain the variance in the data given the presence of additional model parameters. So it seems that we can justify resolving or using a more complex model to explain the variance in the data. So now to the second earthquake, we were looking at the Kaikoura event. Here we're using the displacement maps from Zinkital 2019, and we've measured displacement for almost all of the faults for this event. We have about 45 out of about 49 earthquakes, so it's a very complicated event with slip vectors with rakes that span almost all the different orientations from right lateral, normal, left lateral thrust. And so this provides a pretty good event to try and look for variations in stresses, given it's such a complex event. So here, this is our stress result for the homogeneous stress model. We find that sigma 1 is near horizontal and trending west-northwest, and an R value around 0.1, suggesting it's a Andersonian strike slip stress regime. And so here we find a reduced chi-square value of about 1.5, which shows that there's still some unexplained variance in the data that the model can explain. Overall, we have quite a poor percent of variance reduction of around 47%. And again, we find a quite high static frictional coefficient of 0.7, indicating a fairly strong fault system overall. So what we can do again is given that there are some unexplained variance in the data, we can partition the rupture into two. We partition the rupture into two different domains, into the west and eastern half. And so here's a stress inversion result for the western zone and the eastern zone. We find that the F-test can actually reject the null hypothesis, indicating a more complicated model is likely justified, or we can reject the notion that a more complex model does not provide a better fit to data given the increased number of model parameters. Here we don't find a significant difference in the R ratio values, but there is a slight rotation in sigma 1 for the western zone. Sigma 1 seems to be rotated a bit more northwest than in the eastern zone. And this seems to be generally consistent with what was found in the background seismicity, where along the eastern part of the North Island, the sigma 1 is trending almost east-west, in some places trending just south of west. And further west in this western zone, sigma 1 seems to be trending in a more northwest direction. And so it seems for these two zones here, they seem to be consistent with the co-seismic stress field. And so we found a percent of variance reduction of about 50%, but we are unable to justify further partitioning data into three zones. So with that, I'll leave it with the conclusions. Thank you very much.